as it explains the enduring legacy of Voyager missions, which surpass all records, surpassing any other space mission in history, in fact.
As it talks about the lasting effects of the Voyager missions, which are better than any other space mission ever. In fact, the Voyager mission is one of NASA's most successful and longest running. 50 years after it was launched, Voyager would go off and then miraculously come back on, but right away it would send a scary signal. What did the Voyager find, and why are scientists worried about it? Watch out to find out. And Gary Flandro is one of the people you might not have heard of when it comes to one of NASA's best missions. Flandro, on the other hand, was a very important part of figuring out where the Voyager 1 spacecraft would go. His ideas and calculations made it possible for the Voyager missions to go well. These missions have since become famous in the history of space exploration. In the middle of the 1960s, Flandro made a huge discovery while working at NASA's Jet Propulsion Laboratory, JPL. He found a rare alignment of the outer planets Jupiter, Saturn, Uranus, and Neptune that would happen between the late 1970s and early 1980s. This alignment only happens about once every 175 years, so it was a one-of-a-kind chance for a spacecraft to use gravity to move from one planet to the next, saving time and fuel. In the idea of gravitational assist, also known as the slingshot effect, a spacecraft uses a planet's gravity to speed up and change its path. As the spacecraft gets closer to a planet, it falls into its gravitational pull and speeds up. As it moves away, it keeps a lot of this extra speed, so by carefully planning its path, it gets a boost. Engineers can use this effect to make spacecraft go on long trips that use little fuel. Recognizing the possibilities of this planetary alignment, Flandro proposed a grand tour expedition. This mission would send a spaceship on a journey around the solar system, using gravitational assistance to visit all 4 of the outer planets. The trajectory he proposed would allow a spacecraft to pass by each planet in sequence, gathering data and sending it back to Earth. The consequences of Flandro's research were substantial. Not only would such a mission deliver unparalleled data about the outer planets, but it would also do it in a fraction of the time that would be required if each planet were targeted separately. Furthermore, the fuel savings from using gravity assistance meant that the mission could be achieved with the technology and resources available at the time. However, despite the apparent benefits, there were also considerable obstacles. Plotting a trajectory that would take advantage of the gravitational help from numerous planets needed careful calculations and timing. The spaceship would need to arrive at each planet at exactly the right time and in the proper position to acquire the requisite boost to continue on to the next destination. Any miscalculation or technical failure could result in the mission's failure. Moreover, the large distances involved caused issues for communication and data transmission. The spacecraft would need to be equipped with modern sensors capable of functioning in the harsh environments of deep space and transmitting data across billions of miles. Despite these limitations, Flandro's concept was welcomed with enthusiasm at NASA. The potential scientific rewards of the Grand Tour were too enormous to ignore. However, because of budget limits and the technological obstacles involved, NASA chose to scale back the project. Instead of one spaceship visiting all 4 planets, 2 spacecraft, Voyager 1 and Voyager 2, would be launched. Voyager 1 was tasked with flybys of Jupiter and Saturn, whereas Voyager 2 would also visit Uranus and Neptune, provided its earlier missions were accomplished. How did the Voyager 1 launch? The launch of Voyager 1 on September 5, 1977, was a historic milestone for humanity and space exploration. It marked the beginning of an epic mission that would take the spaceship to the outer planets and beyond, exposing new wonders and secrets of the solar system and interstellar space. Voyager 1 was part of the Voyager mission, a NASA initiative to explore the outer solar system utilizing 2 identical spacecraft, Voyager 1 and Voyager 2. The initiative was prompted by the discovery of a rare planetary alignment of Jupiter, Saturn, Uranus, and Neptune that would occur in the late 1970s and early 1980s. This alignment offers a rare chance for a spacecraft to exploit the gravity of each planet to accelerate its speed and shift its direction, saving time and fuel. The concept of using gravity help, or the slingshot effect, was not novel. It had been utilized earlier by other spacecraft, such as Mariner 10, which sailed by Venus and Mercury in 1974 to 1975. However, the Voyager missions were the first to employ this technology to visit numerous planets in sequence, establishing a grand tour of the outer solar system. The Voyager spacecraft was conceived and built at the JPL in California. They were based on the Mariner spacecraft design, but with various alterations and upgrades. They took 11 science tools with them to study the rings, magnetic fields, atmospheres, radiation environments, and moons and rings around planets. They also brought a special gift with them, a golden record with sounds and pictures of Earth. This was meant to send a message to any alien intelligence that might come across them. Voyager 1 was launched from Cape Canaveral Air Force Station in Florida on a Titan III-E Centaur rocket. A problem with the rocket's tracking system caused the launch to be pushed back by 2 weeks. Voyager 1 finally took off from Launch Complex 41 on September 5, 1977, and flew high into the sky. Voyager 1 went faster and for a shorter distance than Voyager 2, which was launched 2 weeks before it. In November 1977, it got to the asteroid belt and went right through it. The journey to take pictures of Jupiter began in April 1978, when it was about 165 million miles, 265 million kilometers, away. The closest point that Voyager 1 got to Jupiter was on March 5, 1979, when it was about 217,000 miles, 349,000 kilometers, away. Pioneer 10 and 11 were the first spaceship to visit Jupiter, but Voyager 1 was the first to find out many of its secrets and catch people by surprise. The first Voyager spacecraft flew by Jupiter on March 5, 1979. It was about 217,000 miles, 349,000 km from the planet's clouds. It made many discoveries and findings that changed the way we think about the gas giant and its moons during its encounter. One of the most interesting things that was found was that Jupiter has a thin ring around it that can't be seen from Earth. The ring is made up of dust particles that are likely thrown out by meteoroids hitting the inner moons. Jupiter's center is about 50,000 miles, 80,000 kilometers, away from the center of the ring, which is less than 19 miles, 30 kilometers deep. Voyager 1 also found 2 new moons, Thebe and Metis, that are orbiting inside the ring. Their widths are about 62 miles, 100 kilometers, and 25 miles, 40 kilometers, respectively. They are small and have odd shapes. One of Jupiter's 4 big moons, Io, has volcanoes that were found to be active. Voyager 1 took beautiful pictures of clouds of gas and dust rising from Io's surface. This shows that Io is the most geologically active body in the solar system. The volcanoes are heated by the tides, which happen because Jupiter's large moons Europa and Ganymede are in resonance with Ios. Io has a thin atmosphere made of sulfur dioxide that comes from the volcanoes. Some of this gas escapes into space, making a donut-shaped cloud of ions that circles Jupiter. Voyager 1 also recorded the strong radiation belts around Jupiter. These belts are made by Jupiter's strong magnetic field interacting with the solar wind. The radiation belts are made up of charged electrons and protons that can hurt spacecraft and make future trips more dangerous. Voyager 1 saw lightning and the northern lights in Jupiter's atmosphere. It also picked up radio waves that change as the planet spins. When electrons move along the lines of the magnetic field and interact with the plasma in the magnetosphere, radio waves are sent out into space. Voyager 1 also looks at Europa, Ganymede, Callisto, and Amalthea, some of Jupiter's other moons. It was found that Europa's surface is smooth and icy with few craters. This suggests that Europa is geologically young and may have an ocean of liquid water below the surface. Also, it was found that Ganymede has its own magnetic field that is part of Jupiter's magnetosphere. It also discovered that Callisto's surface is very old and full of craters, which means it hasn't been through much geological activity. What it also found was that Amalthea is oblong and has a reddish color, which may be because of sulfur from Io. After leaving Jupiter, Voyager 1 went to Saturn, which was its next stop. It got to Saturn on November 12, 1980, after going by the planet about 77,000 miles, 124,000 kilometers away. It also flew by Titan, Saturn's biggest moon, at a distance of about 4,030 miles, 6,490 kilometers. This was the first time a spacecraft had studied Titan's thick atmosphere. Voyager 1 was the second spacecraft to visit Saturn, after Pioneer 11. However, it was the first to find out many of the planet's secrets and fun facts. The first Voyager spacecraft flew by Saturn on November 12, 1980. It was about 77,000 miles, 124,000 kilometers from the planet's clouds. During its encounter, it made a number of discoveries and observations that changed the way we think about the ringed planet and its moons. One of the most interesting things found was that Saturn has a new ring called the G ring that can't be seen from Earth. The G ring is made up of very small particles that are likely thrown out by meteoroids hitting the inner moons. The G ring is very faint and very thin. Its width is about 4,700 miles, 7,500 kilometers, and its inner edge is about 104,000 miles, 167,000 kilometers, from Saturn's center. Voyager 1 also found 5 new moons: Prometheus, Pandora, Atlas, Epimetheus, and Janus. These moons orbit around the rings or are close to them. With diameters that range from 40 miles, 64 kilometers, to 90 miles, 144 kilometers, they are small and have odd shapes. These celestial bodies are commonly referred to as shepherd moons due to their role in preserving the morphology and stability of the rings through their gravitational impact. Another significant revelation was the intricate configuration and motion of Saturn's rings, consisting of billions of ice and rock particles varying in size from minuscule particles to large boulders. Voyager 1 observed that the rings exhibit non-uniformity, characterized by the presence of gaps, waves, braids, spokes, and kinks, which arise from the interactions between the particles comprising the rings and the moons. Voyager 1 detected a void within the ring, which can be attributed to the orbital resonance with the lunar celestial body known as Mimas. A wave pattern in the B ring was also observed, which can be attributed to the orbital resonance with the moon Janus. Additionally, it detected transient spokes in the B ring, which could be attributed to the electrostatic charging of the ring particles caused by lightning in Saturn's atmosphere. Additionally, Voyager 1 conducted measurements of Saturn's magnetic field and magnetic sphere, which are produced as a result of the planet's rotational motion and its interaction with the solar wind. The magnetic field exhibited by Saturn bears resemblance to that of Earth, albeit with significantly greater strength and inclination. Saturn's magnetic sphere encompasses a vast expanse of space that encircles the planet and extends beyond its rings. The plasma particles present in this substance are derived from the atmosphere, rings, and moons of Saturn. Voyager 1 observed various phenomena such as auroras, radio emissions, plasma waves, and energetic particles in Saturn's magnetosphere. Voyager 1 also detected Titan, Enceladus, Nemesis, Tethys, Dione, Rhea, Hyperion, Iapetus, and Phoebe, which are the other moons of Saturn. It found that Titan has a thick atmosphere made up of methane and nitrogen. Titan is the only moon in the solar system with a thick atmosphere. They also found that Enceladus has a smooth, bright surface with few craters. This suggests that it is geologically active and may have an ocean of liquid water below the surface. They also found that Mimas has a huge crater called Herschel that is about a third of the way around the planet. It also found that the difference between Iapetus's dark and bright halves is very noticeable. Voyager 1 passed NASA's Pioneer 10 on February 17, 1998, to become the farthest man-made object from Earth. The 16th of August, 2006. 19 billion kilometers, or 9.3 billion miles, is how far away it was from the Sun. Voyager 1 is now about 15 billion miles, 24 billion kilometers, away from Earth, making it the farthest man-made object from the planet. It was the first man-made object to cross the heliopause and enter interstellar space. Voyager 1 can still talk to Earth, even though it is very far away and very old. How is it possible? There are radio systems in space called the Deep Space Network, DSN, that can help with this. A high-gain Cassegrain antenna with a diameter of 3.7 meters, 12 feet, makes up Voyager 1's radio communication system. It can send and receive radio waves through the 3 DSN stations on Earth. The platform that holds the antenna can turn and point in any direction in space. There are two frequency bands that the antenna can send and receive signals in. The S-band has a wavelength of about 13 centimeters, and the X-band has a wavelength of about 3.6 centimeters. You send commands and engineering data over the S-band. Images and scientific data are sent over the X-band. The DSN is a group of large radio antennas spread out around the world that can talk to spacecraft in deep space. DSN has places close to Goldstone, California, Canberra, Australia, and Madrid, Spain. These spots are spread out pretty evenly around the world, so no matter which spot you are, you can always see Voyager 1 because of the way the Earth spins. There are several antennas at each site, with the biggest one being 70 meters across. It takes this antenna to pick up the very weak signals from Voyager 1. These signals are 20 billion times weaker than what a digital watch needs to work. Communication between Voyager 1 and Earth doesn't happen right away. It takes time based on how far apart they are. Light moves at the speed of sound, which is about 186,000 miles per second, or 300,000 kilometers per second. But because Voyager 1 is so far away, it takes about 21 hours for a signal to go from Voyager 1 to Earth and back again. This means that after NASA sends a command to Voyager 1, it has to wait 21 hours to hear back that the command was done. In the same way, it takes NASA 21 hours to receive data or pictures sent by Voyager 1 to Earth. The continuity of communication between Voyager 1 and Earth is contingent upon various factors, including power availability, data rate, antenna pointing accuracy, and sources of interference. Voyager 1's radioisotope thermoelectric generators, known as RPGs, have a finite power output and gradually degrade over time. Hence, it must determine the order of importance for the instruments and systems to be utilized at any given moment. The data transmission rate of Voyager 1 diminishes as it travels further from Earth due to the decline in signal intensity with increasing distance. The communication quality is influenced by the accuracy of antenna pointing, as even a minor deviation from the optimal direction can lead to signal loss. Furthermore, it is important to note that communication can be subject to disruption caused by external sources, including but not limited to the Sun, other planets, and other spacecraft. Notwithstanding these obstacles, Voyager 1 persists in transmitting valuable data and images to Earth through its radio communication system and the DSN. Furthermore, it consistently receives instructions and updates from the planet to guarantee its optimal operation and efficiency. Talking back and forth between Voyager 1 and Earth is an amazing feat that shows how creative and curious people are. This is also proof of Voyager 1's strong partnership with NASA, which has been going on for more than 40 years. But what is going on with Voyager 1 in space between the stars? There is a place in space between the stars in a galaxy called interstellar space. It is not empty. It is full of gas, dust, cosmic rays, neutrinos, photons, dark matter, and other types of matter and energy. But these parts are very few and far apart, which makes interstellar space as close to a vacuum as it can get. One way to show where the edge of interstellar space is by looking at how the Sun and other stars affect the space around them. The solar wind is a steady stream of charged particles and magnetic fields that come from the Sun. It makes a huge bubble around the solar system. This bubble is called the heliosphere, and it keeps most of the radiation and particles from other stars from hitting the planets. The heliosphere is situated at an approximate distance of 122 degrees Celsius from the Sun, with 1 degree Celsius representing the average distance between the Earth and the Sun. Located at the periphery of the heliosphere, the solar wind comes into contact with the interstellar medium known as ISAM, which refers to the substance and energy that occupy the space between stars. The interplanetary system, ISM, applies force on the heliosphere, resulting in the generation of a shock wave that causes the solar wind to decelerate from supersonic to subsonic velocities. The shock wave in question is commonly referred to as the termination shock, which signifies the initiation of a turbulent area known as the heliosheath. The heliosheath is the region where the solar wind undergoes mixing with the ISM, resulting in increased temperature and density. The heliopause, which delineates the outer boundary of the heliosheath, signifies the termination of the Sun's sphere of influence. The interstellar space located beyond the heliopause is characterized by the dominance of the ISM over the solar wind. The primary objective of Voyager 1 was to access interstellar space and investigate its characteristics. Nevertheless, the identification of the heliopause crossing proved challenging due to the absence of distinct signs or indicators denoting this transition. In order to assess a range of parameters including plasma density, magnetic field strength and direction, cosmic ray intensity, and plasma waves, Voyager 1 was dependent on its instruments. In May 2012, Voyager 1 detected a sudden surge in cosmic rays, which are high-energy particles originating from beyond the solar system, indicating its approach to interstellar space. This observation implies that Voyager 1 was transitioning from the heliosphere's protective shield to a region characterized by a higher concentration of cosmic rays. The second indication emerged in June 2012 when Voyager 1 observed a reduction in solar wind particles, suggesting a departure from the origin of said particles. Nevertheless, this observation does not provide definitive proof of venturing into interstellar space, as there may exist additional variables that influence the density of solar wind. The third and ultimate indication was observed in August 2012, when Voyager 1 detected a significant alteration in plasma density and the direction of the magnetic field. Plasma is a gaseous mixture of charged particles capable of conducting electric currents and producing magnetic fields. The plasma density of Voyager 1 was assessed through the utilization of its plasma wave instrument, PWS, a device designed to detect oscillations or vibrations in plasma resulting from diverse phenomena. Voyager 1 observed a significant rise in plasma density on August 25, 2012, with values escalating from approximately 0.002 per cubic centimeter to approximately 0.08 per cubic centimeter. Consequently, Voyager 1 had traversed a region characterized by significantly higher plasma density compared to the heliosphere. Voyager 1 also used its magnetometer mag to measure the strength and direction of the magnetic field. This device can pick up changes in magnetic fields caused by moving charges or electric currents. Voyager 1 saw a change in the direction of the magnetic field by about 20 degrees on August 25, 2012. This meant that Voyager 1 had moved into an area with magnetic fields that were not aligned with those in the heliosphere. These two measurements proved that Voyager 1 had gone into interstellar space for the very first time in recorded history. But this confirmation didn't happen right away because Voyager 1's signals had to travel 17 hours to reach Earth because it is so far away. Scientists also had to look over and confirm Voyager 1's data for a few months before letting the public know about this important event in September 2013. However, we won't be able to talk to Voyager 1 forever. The reason is that Voyager 1 can only hold so much fuel. It will run out of power at some point, and it will be left to wander the galaxy by itself. NASA says that Voyager 1 will have enough power to run one instrument until 2025. After that, it will have to turn off its radio transmitter and be quiet for good. But even after that, Voyager 1 will keep traveling through interstellar space, carrying a golden record with sounds and pictures of Earth as a message to any alien intelligence that might come across it. Additionally, it will always be a reminder of how curious, creative, and resourceful people are,